All right, let's try to finish this chapter. Of course, remember I still have to do the mathematical stuff. The mathematical equations about the speed of light and the wavelength and the frequency, and also a little bit of Snell's law, which of course you get in lab, but I want to repeat it here. All right, so rainbows. All right, so if you've ever, of course, you more than likely have seen a rainbow. Um, it's actually interesting that you have to be in a situation where the sun is behind you. There has to be rain. Basically on the opposite way. Like in other words, if the sun is behind you, just like this picture is showing, the rain would be in front of you, and so you look up and you see a rainbow. All right. So what exactly is going on? What happens is when the light gets into the raindrop, it is actually being because red light is has a slightly different index of refraction than blue light. And that, remember, that's called dispersion. The red light and the blue light, and in fact all the colors of the rainbow separate. And so when you look, you see a rainbow. And actually sometimes you'll actually see what's called a double rainbow. All right, so an observer, let's see, is in a position to see a single rainbow from one drop. Your rainbow is slightly different from rainbows seen by others. Everybody sees their own unique rainbow, actually, because you're not looking at the exact same drop of water at the same time. Let's see, and then discs with a bow that's brighter because there's an overlap. You get multi refraction. So if you ever see a double rainbow, which is actually a pretty rare thing, um, and oh yeah, let me just state one. Oh, we'll look at this picture right here. If you've ever seen a rainbow on a mountain, you can actually see the full circle, right? I mean, it's always like an arc. Um, and if you're up on a mountain and you happen to see a rainbow and you're high enough, of course, you can see the full circle of the rainbow, which is kind of an interesting thing. It would be a circle. It wouldn't be a bow anymore. But anyhow, this is what's called a double rainbow. So you can kind of see this. The second rainbow is always fainter. And notice what's going on here. So let's say you're looking from the left hand side. You see a blue to red. But then if you look at the second rainbow, although you can barely see it here, the colors are reversed. All right, so you're seeing from red to blue, and that is, let's see, are they showing you in this picture? Kind of, no. All right, anyhow, so that's compared with the primary rainbow. The secondary rainbow has the colors reversed, right? Oh, wait a second. That's all. Okay, is dimmer. Yeah, I didn't read the other ones. Has the reverse colors and is caused by two internal reflections. Yes, that's true. All right. So the next one, we're not going to cover too much about this. I just want to mention the fact that light can be polarized. It can be well, it's what's called a transverse wave. So what's waving is perpendicular to the direction of motion. So that's what we mean by transverse wave. This would be this is what unpolarized light is, and so most light when you encounter it is just vibrating in all sorts of directions, and when you have polarizers, you basically filter some of those directions. Like, for example, what polarizers are. Here's a good example of a polarizer is sunglasses, right? That's exactly what sunglasses do. Is that they'll block all the light that's not oscillating, up and down, let's say, or back and forth. And so, it decreases the amount of photons they get to your eye. So this is a good example, right? Imagine like an actual physical wave that's going through, that's going through a fence that's that's vertically up and down, and of course that wave can pass right through. But if you had a wave that was oscillating, side to side, it would never get through here. So this is polarized light, or well, this is not light. Of course, this is just a it's a slinky or something like that. All right, so light from a regular old flashlight is unpolarized, so it goes through. If you pass it through a polarizer, it's basically like a filter that'll only let oscillations in one direction through. So that's the idea of a polarizer. All right, so there's somebody with a polarizer, and then if you hold them at right angles to each other, you'll block all the light. Polarizers occur for waves that are transverse. All right, so that is our chapter. I'm going to next turn to some mathematical examples. All right, so here are some of the equations that we're going to use. So you have the wavelength is using the symbol lambda, and so that's measured in meters. The frequency is a quantity that's measured in, so that's Hz, capital H, lowercase z, that's called hertz. And there's a relationship between hertz and the frequency and the period. So the period is the amount of time that it takes a wave to complete itself. That's measured in seconds. So the wavelength, by the way, of course, is the distance that the wave travels when it completes itself, right? So and then v is the velocity for all electromagnetic radiation or any form of light. The speed of light is 3 times 10 to the 8th meters per second. And so the frequency is 1 over the period. And so this thing called hertz is really just 1 over seconds, or another way of saying it is cycles per second. All right, so the other thing that I wanted to write is, all right, and I just want to make sure that it's clear. V is the velocity in the material. C is the speed of light in a vacuum. All right, so the index of refraction is the speed of light in a vacuum divided by the speed of light in the material. All right, so n is a constant. There are various values for it. Like 1.4 for most glass. All right, so in fact, let's say that it's let's say that the index of refraction is 1.4. So I'm using a specific example. Let's say this is the index of refraction for glass. All right, glass. So the question might be, how fast is light in the glass? What's the velocity? So we're going to solve for v, and we're using this equation right here. All right, so in this particular case, the index of refraction of glass is well known. There are different types of glass, but let's just say that this particular glass is 1.4. All right, and so that's equal to the speed of light, which is of course 3 times 10 to the 8th meters per second. That's the speed in a vacuum divided by the velocity in the material, right? And so if I want to figure that out, I just multiply both sides by v, and so there's v, and then I'll put a v right here. The v's cancel, and then I'm going to divide both sides by 1.4. Right, so divide by 1.4. All right, there we go. So the velocity is going to equal 3 times 10 to the 8th meters per second divided by 1.4. 1.4. All right, so here, let me get out see if you can see this calculator. Let me move it over just a bit. All right, there we go. All right, and so it's 3 times 2, so 3, you got to know how to do this in your calculator. So that's 3 times 10 to the 8th divided by 1.4. So this would be the velocity. Let's say, so there's the decimal point right there. All right, so I'm gonna do 2 places past the decimal. Okay, so let's write it in scientific notation, right? So this would be 2.14, right? And look, so 2.14. Well, where's the decimal? Decimal's right here, so it's 1, 2, 3, 1, 2, 3. And so it's 2 more, right? So 2.14 times 10 to the 8th, right? So that's, here, let me put this off to the side. So this would be 2.14, let me rewrite it. So 2.14, that's a decimal, times 10 to the 8th. And of course, it's meters per second. All right, so notice this speed is, of course, less than the speed of light. The speed of light is 3 times 10 to the 8th meters per second. All right, in a vacuum, right? So this would be the speed of light in glass. All right, and so you could do various problems. Here, let's see. Do I have some different indexes of refraction? So let's see. See if I get some of these. How about a list of them? No, that's not what I want. I just wanted a list of. Here, let me pause. All right, so these are some different materials. I just Googled this. So one thing to note: air is almost 1. Usually, we just, in fact, you usually use air. The index of refraction is 1. Although, just keep in mind, it is slightly more than 1. So it does, the photons don't interact with the light very often. All right, so and then for water, for example, it's 1.333. So let's do an example with water. Okay, so there's some other indexes of refraction. There's the one for diamond. Diamond, it's 2.417. So that's extremely. Oops. All right, so let's use this example. So the index of refraction for fresh water is 1.333, and that's of course the speed of light in a vacuum divided by the speed of light in water. So the velocity. So you just rearrange this equation and solve for velocity. The velocity in water is going to be the speed of light divided by 1.333. And notice I said the speed of light. It's, of course, the speed of light in a vacuum. But it gets tiring saying that all the time. So usually people just say the speed of light. So it's 3 times 10 to the 8th meters per second. That's an 8. Divided by 1.333. All right, so remember this index of refraction is just a number. All right, so let's try to do this problem real quick. All right, so it's going to be 3 times 10 to the 8th divided by 1.333. All right, so this is the speed. All right, again, we're going to round it to 2 places past the decimal. So it's going to be 2.25. So 2.25 times 10 to the 8th. All right, so that's what this is. So 2.25 times 10 to the 8th. And of course, that's in meters per second. All right, so there's another example. Let me set up Snell's law. So here's an example of Snell's law. So it's n1 times sine of theta 1 and is equal to n2 times sine theta 2. And so this is 2 different media, right? So the air, a beam of light is going from air to water, right? So that's a good example. So n1 is 1 for air, and then for water it's 1.333. All right, let's do a quick example. Let's say that theta 1 is 30. What would be theta 2? All right, so this is how you solve this. Theta 2, remember, here, let me move this a little bit. Theta 2 is going to be this angle right here. Oh, man, this angle right here. It's going to be smaller than theta 1. So remember, theta 1 was 30 degrees. So theta 2 is going to be the inverse sine of the sine of 30 divided by that. All right, so let's do this in our calculator. All right, so the sine of 30 is 0.5. All right, so I'm just to make it shorter, we'll do that. 0.5 divided by 1.333 equals, and then you do trigonometry for this calculator, inverse sine. So it's 22 degrees. So that would be the answer. 22 degrees would be theta 2.